Dando continuidade às palestras da segunda semana de aplicações operacionais ao preparo e emprego, o próximo palestrante será o professor Dr. Girum Urgessa, da George Mason University. Currículo do professor Dr. Girum Urgessa.
Professor Girum Urgessa. Professor Girum Urgessa is a Fellow of the American Society of Civil Engineers and an Associate Professor of Civil Engineer at George Mason University in the U.S. His research interests include dynamic response of structures subjected to air blast, projectile impact, progressive collapse, and underwater explosions. His research is funded by the U.S. Department of Defense, the U.S. National Science Foundation, and the other organizations. Professor Urgessa is the recipient of the 2022 John Tupps Presidential Medal for Faculty Excellence in the Teaching at George Mason University.
Convidamos o professor Dr. Girum Urgessa para iniciar a palestra intitulada Underwater Explosion Effects on Crooked Columns.
Thank you very much. Is it already 12 p.m.? I was going to say boa tarde. Well, first of all, thank you so much for inviting me to come here. I was here at the SIGE conference 6 years ago, and it was a big conference, but I'm actually very much, impressed to see how big it's getting every year. So again, thank you so much for your invitation here. When I came here 6 years ago, I gave a presentation on some of our work at George Mason, looking at the effect of blast or air blast on reinforced concrete structures. This could be concrete masonry unit walls or concrete columns or concrete slabs. And I had the pleasure to work with Lieutenant Colonel Fausto here when he was in the United States at George Mason. I co-advised him with Professor Fritz, who's at the back here, and I have kept that connection very strong. We have several publications together. And when he invited me this time, I'm giving you guys an update of what we have been doing in the past 3.5 years, looking at, instead of air blast, now we're looking at underwater explosion. So in terms of the outline of my talk, I think I'm clicking too fast. So I'll tell you a little bit about myself so you can, I'm sure some of you are saying, he speaks English, but he has a little bit of accent, right? So I'll tell you a little bit about my background. And then whenever I give presentations, particularly to non-military type conferences, people will ask me, why do you study explosions, right? Of course, for you, I don't have to convince you why studying explosions is an important endeavor. And then after that, I will talk about our project overall. Our project is unclassified, so we don't have a lot of data. So I'll walk you guys through how we were able to validate some of our models and also some of our programming. But the good thing is, in the PowerPoint slides, I'm not going to show you too many equations, so I'm not going to make it boring for you. And then I have a couple of slides on conclusions. But before I do that, because this is my second time here, I've been learning a little bit of Portuguese. And now I know my foods very well. So I can say frango, beefy, and then my drinks like cafe and chá. So I'm getting better at it. So my goal would be the next time you invite me, maybe I'll give a 10-minute presentation in Portuguese, not Portuguese. So that's the goal I'm working on. In terms of my education background, I'm originally from Ethiopia. It's a country in East Africa. I'm sure most of you know where that country is. I received my Bachelor's of Science from Addis Ababa University and then moved to the United States. My master's and PhD was at the University of New Mexico in Albuquerque, New Mexico, very close to Texas, Arizona, Southwest. And then I had industry experience. My first industry experience is working for an architectural engineering firm, designing the small-scale buildings, nothing fancy, schools and healthcare facilities, up to 3 stories high, not complicated. But then after my PhD, I worked for a research engineering company called Weidlinger Associates. They were looking at very specialized problems. For example, what happens if you have an explosion in the New York subway? What are the impacts? So we've been looking at very specialized work. That's where my interest in blast or explosion started, working for this company. This company is now bought by another major company, a global firm called Thornton Tomasetti, and they do all kinds of engineering consulting. Now, I joined George Mason University in 2007, so I have been a faculty member for 17 years. So I'm telling you, just to tell you, I'm old. Okay, but I have also 1 semester experience at another institution. I had a leave. It's called Howard University. It's also located in Washington, D.C. In terms of the research relevance, usually the way I like to frame the research relevance is from a policy perspective. Okay, so in the United States, the Federal Emergency Management Agency has published a document called the National Preparedness Report. I think this is a report that guides not only the governments, but local communities or like cities in organizing an effort to address issues associated with threats and hazards. And I try to put the first bullet point which says the whole community approach. I think everybody is responsible to participate in making sure that our infrastructure and also our personnel are safe or have the ability to respond when we have hazards. Okay. Now, this report is divided into 5 different frameworks, and I try to list here for you in the bullet point. Let me see. So the first one is prevention. In some cases, you may have an imminent danger, and then you have to prevent an act from occurring. In some cases, the framework may be protection. Maybe you're protecting or retrofitting schools. And in some cases, it could be mitigation, meaning the event will happen, but you're trying to reduce the fatalities, for example. That could be mitigation. And then, of course, when an hazard occurs, you have to be able to respond. And recovery would be, you have to, again, plan on rebuilding your community again. So these are 5 different frameworks that are found in this report. But then the question is, how do we define threats and hazards? So maybe let me ask you guys this. What do you consider is a threat or a hazard for a given community?
Was a sort of force, wall, damage.
So what would be a source of the damage? Like, can you give me an example of something that can cause a source of damage?
It can be the security issues or
Right.
Security, like intelligence.
Okay, so maybe terrorist attacks. Okay.
And in safety, like the machine that is working properties, maybe those on it.
Okay. And yeah, I think those are good classifications, good umbrella. But I was looking for, whenever you think about buildings, bridges, infrastructure, even outside of military, what are the sort of things that are a threat to that infrastructure?
Some space of blood recently in the sun.
Okay, so flooding, right? Or earthquake, somebody mentioned earthquake. So those are more natural events, right? So the way Federal Emergency Management Agency has a very nice plot, I'll show you here. So there is 3 different classifications here. The one you see on the green side, on the left, is natural hazards. Of course, we have to design our structures for natural hazards, and this includes, the sort of stuff we talked about, the flooding, the earthquake, tsunamis, or fire, right? That's a problem as well. And there's a list that will come later on. But you can see that that's actually our main design criteria in most infrastructure design. Now, on the top right side, you'll see what are called technological or accidental hazards. For example, you may have a dam failure that's not necessarily from a malicious attack. It could be a simple crack that grew through years, and you may have a dam failure down the road, right? So it could be an accidental failure. There could be an accidental chemical substance release without a malicious intent. So those are classified here as technological or accidental. But then on the bottom down here, you can see that, well, humans also are responsible for causing malicious, or for being involved in malicious activities. And one of the areas that we will include is explosive terrorism. So one of my dear friends, actually, who's originally from Sao Paulo, his name is Celso Ferreira, is my colleague. He is an expert in studying the effect of structures subjected to hurricanes. He's from this area. And so, my work can be easily explained in this category. Okay. Now, in the United States, there is a survey that's always sent to states and local communities, asking them, what are you afraid of? What are you afraid of this year? And as you can see in this survey, which is in 2022, most communities are worried about cyber attack. Of course, we are coming off of the post-pandemic era, right? So there's a pandemic concern there. But, communities also concerned about explosive devices is not small, okay? Because there's sometimes a perception that explosive devices are only a concern for the military, but the local communities also really are concerned about, some malicious acts using explosives. So this is just a data to show you the number of communities who responded that an explosive device could be a problem in their communities. Okay. Now, I'm part of an organization called American Society of Civil Engineers. That's a parent organization. We have a policy document called Policy 389, looking at how we mitigate the effect of structures or infrastructure for natural hazard and human cause hazard. And as part of that list, in the old days, it was always including natural hazards, and they used to call non-natural hazards. But nowadays, we are giving more specifics. For example, in human-induced hazards, we have explosives listed. So there's a group of civil engineers who will be looking at explosive effects on infrastructure. Okay. So hopefully this gives you the kind of the policy or the umbrella for my research work outside of, again, the military needs. And then what I will do next is tell you a little bit about our underwater explosion research at George Mason. We have been working on this for the last 3.5 years. I'll be using the word ANDEX instead of underwater explosion. It's a shorthand. And overall, the project was funded by the Department of Defense. There's a division called the Defense Threat Reduction Agency. The need was to determine high quality pressure data when we have explosions underwater. At George Mason, we had a simulation platform called FE-Flow. FE-Flow has been validated for many years to capture the impact of air explosions on structures. So the goal here is, can you expand that simulation to capture underwater effects. Okay. Just a little bit of background about FE flow. Again, developed at George Mason University. The main developer is Professor Renal Lohner. So anything I do here is, I'll give credit to Dr. Lohner. On this project, we are working together, but he's original developer of FE flow. Now, FE flow is able to model anything that is compressible or incompressible. You're able to do that. And also it has several equations of state. Equations of state mean what is the characteristic of the relationship between pressure and volume for water or for air or for explosives. And then the program was extensively benchmarked with test data. So the goal is, again, to expand this for underwater explosion. Now, just to give you some pictures from previous work, this is a picture showing you what happens when you have a blast in a downtown of a bigger city. So you can use FE flow to actually predict how the blast pressure is spreading. Okay. Or Professor Lohner also has modeled another one, which is a pressure on a space shuttle. Okay. So again, you can use FE flow to characterize the different pressures for this. So our task was, can you expand this again for underwater situations? Okay, so for this particular project, this is a research team. We have 2 professors, 1 postdoc, 1 PhD, and 1 MS. And the reason I like to show this is my PhD student, Jacob Sanders, is not here, but we are 5. But you'll be surprised, all 5 of us were born in different continents. So I'm born in Africa, Professor Lohner is born in Germany, our postdoc, Lin Chua Li, is born in China, and the last person you see, Facundo, is actually born in Argentina. So we have representation from South America, and my PhD student was not here. Jacob Sanders is from the US. So you're looking at 5 different continents, 5 different people working on a project together. So how did we start to look at underwater explosion? The first thing we did is we started to look at, okay, do we have the capability to predict how much pressure will be generated in a water body without having any structure? Because you don't want to jump into looking at the structure without understanding how pressure is generated just underwater, okay? So we call that free field underwater, okay? There's no structure exists. And I'll talk about a little bit about the free field underwater case. Now, when you compare explosions happening in air versus underwater, the situation underwater is much, much complicated. And the reason being, as you can see here in this plot, you have an explosion. An explosion will start. The pressure will expand. If this is your point of interest, there will be a direct shock wave coming to your point of interest. But then some of the pressure will go up to the air-water interface. And when it hits the air-water interface, because of the density difference between the water and the air, you will have a reflection back in the water. So again, your point of interest will see another wave coming here. Also, if you have a shallow water, you may have some reflection from your ground surface coming to your point of interest. So when you're trying to model this, you'll be tracking so many different waves and their interaction. So compared to air explosion, there is an additional layer of complexity when you're looking at underwater explosion. And later on, I'll show you our simulation for a free field case. So how do you determine free field pressure? Well, you can do experiments. Some researchers have tried to do experiments in a very large water tank. They just put, in a very large water tank, you fill it with water, and then you suspend an explosive, and you put sensors at different distances, and then you can measure how much pressure is coming to your point of interest. We have seen some people doing a test in a quarry, maybe abandoned mines. They fill it with water, and then they put sensors at different distances to capture pressures. Now, of course, there are some researchers in the old days who have done a lot of these tests and come up with what are called empirical equations that will allow you to predict how much pressure you have just knowing the explosive weight and the standoff distance. And nowadays, we also rely heavily on our computer simulation, right? So computational fluid dynamics, using equation of motion transports in the water body. Okay? So what we did first is we looked at existing literature. There's a very good work done in South Korea by researchers Moon et al., relatively recent work. They have tested underwater explosion in a 22-meter diameter tank and 15-meter deep. So, again, if you think about the size, it's huge. 15 meters is like 5 stories, right? More than 5 stories. So what they did is they put explosive at 5 meters from the surface of the water tank, and then they put sensors. So they put sensors, so this is the center, and then they put sensors at 2 meters, 4 meters, and 6. And they have quality data. So we used this data to initially validate our very preliminary computational algorithm. Okay? And I'm not going to bore you with the mathematics behind it, but I'll show you some of our results. This is, what an underwater explosion pressure profile looks like. A 1 kilogram TNT at a distance of 2 meters, you're looking at a pressure of about 23 megapascals. Now, so what do you think is, I know everybody knows this, what is the standard atmospheric pressure in megapascals? It's 0.1 MPa. So this is a tremendous pressure. So compared to a standard atmospheric pressure, it's a tremendous pressure. Now, you'll see a few things happening here. There is some re-reflection because this is in a water tank. The pressure will reflect back. But also down the road, after some time, you see a little bit of a peak here. We call this a bubble pulse in underwater explosion. But the most important, again, pressure that we are interested in is this peak pressure value. Okay. Now, as you can see here, these are results for different distances at a standoff of 2, 4, and 6. And clearly, as you move farther away from the explosion, the pressure will decrease, right? Rapidly. Okay. But I want you to remember some of these peak values. So at 2 meters, our peak was 23. At 4 meters, about 13. And then at 6 meters, we have about 7 megapascals. So still a significantly large pressure compared to standard atmospheric pressure. Okay. We also looked at some of the tests that are done in a quarry. One of them that kept coming back and that was used to validate other computational programs is called Quan and Fax. What they did is they filled a quarry 40-meter deep water, and then they put a 60-pound HBX1 charge. Then they put a sensor 25 feet away. I try to give you the conversion units here. I know you use SI units here. So it's about 27 kilograms at 8 meters. Okay, and then they documented the pressure, and the pressure looks like this. Again, tremendous pressure, 16 megapascals. But one characteristic of underwater explosion is it's a very short phenomenon. The pressure is gone in about 2 milliseconds. Okay, so it's a very short phenomenon. It's about 16. We looked at empirical equations. There are empirical equations that say, well, we have a peak pressure and it goes to 0 very quickly. So if we can come up with some very simple mathematical function, people can predict how much pressure the explosion is generating. A very simple exponential function. It is a function of the peak pressure and a constant value for a decay. Okay. Some of the empirical equations that we saw, they go back to 1964. There's a very famous literature by the guy called Cole. But there are also newer empirical equations if you start to look at literature. I'm here showing you just one of the equations from Cole. What Cole did is he did a series of experiments and came up with this equation. So if you know your W, which is your weight of explosive, and R, the standoff distance, you can predict the peak pressure. And similarly, we have this equation called I. In the blast world, I is impulse. If you integrate the area under the pressure time history, you get an impulse time history. So how much energy is being delivered to your system is captured by your impulse. Okay. So we did a very quick comparison between these experimental values, okay, and what the empirical equations are telling us. So as you can see, this is coming from the Moon et al. Large water tank experiment, and these three are from empirical equations. I think a very good prediction for an empirical equation, right? So like at 10, 10, 11. So I think some of these empirical equations do a good job in predicting pressures. We also, again, checked the quarry results. The quarry results from Quan, about 16 megapascals, whereas the empirical equations are predicting a little bit higher, okay, again, within 2 MPa. Okay. So the reason why this is important for us is we just didn't want to expand our computational capability and claim that, oh, it works. We need to have some sort of checking whether our answers are correct or not, right? So it gives us some confidence in our computational simulation, which you will see later on. So what we did is really it took us almost 2.5 years, and this during the pandemic. Our postdoc, Lin Chuan, is very good in computers, and she did most of the programming and validating and testing to see if we can predict this in a 2D and 3D environment, okay? Because the empirical equations have their own limitations. So here is an example from our simulation of an underwater explosion event. Just to give you a representation of the model, we have water here. This is the water-air interface, air and then water. And then we have an explosion here 1 meter below the water surface. And then the total water depth here was 1.5 meters, okay? Now, on the right-hand side, you'll see, instead of showing you the blast everywhere, I'm gonna cut the model halfway, and I'm gonna show you only half of the result because of symmetry. Okay, so we're gonna look at the left side of the pressure expansion. Again, remember this is an interface. Here is air. And this will tell us, the different colors are telling us the magnitude of the pressure, okay? So unlike the empirical equations in our model, we can, do a lot of these simulations. We can check if those empirical equations work outside of the bounds. We can develop new equations by running many of these simulations. But what is interesting for you to see is, I think, if you slow down the movie and look at how the pressure wave expands. So I'm starting out with the explosion here, and okay, this is a nicer picture to show you that the pressure is reflected back, and that the interface now it's gonna come down. A little bit will go to the air, but then it's a complex dynamics here, and that's all captured by computational fluid dynamics. Okay. It looks nice, but really it took us more than 2 years to program these differential equations, okay? And maybe a smaller, just if I show you a still picture, this is a radial expansion of the explosion, and it's about to hit the bottom floor, okay? And then the next one will be after it hits the bottom boundary. You can see that again, that reflecting back and going to the explosion core. Okay. And then the next still picture I'm going to show you is once it hits the interface, the pressure comes back down. A little bit will go to the air, but not a whole lot. Okay. And then here you see the continuation of different waves interacting within the core, outside of the core, and within the water, and some, again, now clearly you can see some pressure going into the air as well. Okay. So once we felt comfortable, at this stage we felt comfortable that we have a tool that will allow us to look at underwater explosion, but what I have shown you so far is there is no structure, right? It's only pressure prediction. So the next step was we have to look into the interaction of a blast wave with a structure. And a structure could be a ship, it could be a dam, it could be a column. But in terms of testing, we started out very simple models. And our project did not involve any experimental work. So we have to depend on published peer-reviewed papers. And we found out a very good paper that looked at the interaction of underwater explosion with cylinders. So in this case, it's an 8-meter cylinder, 0.5 meter in diameter, and then the explosive was put at 0.25 meter. The researchers are Nguyen et al., and they use 8 kilogram TNT very close to the cylinder. Okay, so the pressure values, as you can imagine, would be very, very high. So to zoom in a little bit for you, if you zoom in near the explosive area, this is what the test setup looks like. So what they did is immediately below the charge, they put a sensor. They call it P1. But every 10 centimeters, they put different sensors. So the 6 sensors you see are along the lengths of the cylinder here. Whereas they also put 3 different sensors along the circumference. And the reason being is just to see, for example, if you put a sensor 10 degrees here, is there really a difference between the pressure values? Or if you put a sensor on the side here, 90 degrees, or a sensor 180 degrees, what is the pressure difference that this cylinder will see is captured in their tests? Okay. So what we did is, they did the test, they have the pressure time histories. We used our model and we ran this simulation, and then we have our numerical stations exactly at those locations. We put 9 stations, and we measured our pressure, compared it to Nguyen et al.'s pressure. Okay, and this will show you a quick video. So again, the left one is easier to see. It's a camera trick. We call it Schliering, whereas the real pressure is on the right-hand side. Okay. So again, we can freeze this in time. We can measure, for example, Nguyen et al. Reported pressure only at certain locations where there is a sensor. In our simulation, we can look up pressure at any point that we want. So again, computational fluid dynamics gives you a lot of, power in looking at the different physics of the phenomenon. Okay. Just to show you, I'm not going to show you all 9 plots. It will be boring. You'll be looking at the same plots. But a couple of interesting places. Of course, the first one would be station number 1. That's directly below the explosive. Okay. And as you can see, the pressure is tremendous. It's about 2 gigapascals But remember, this is 8 kilogram at 0.25, okay? Now you may see, well, you have a lot of graphs. The one in black is what's coming from the literature, and these 4 plots are showing our 4 simulations when we're validating what we call number of elements or the size of our mesh for running this model. But again, our prediction was pretty good compared to, again, we didn't do this test. We're using a test that's already done. So we felt, I think our results are reasonably good. On the right-hand side, what you see here is the integration of the pressure time history. It gives you what's called the impulse. That's the total energy delivered in your system. Again, a very good comparison from the literature. I'm showing you another one at station number 3. Remember, station number 3 is 0.1 meters away, so it's at 0.2 meters away. You start to see a reduction in pressure, okay, from about 2.2 gigapascals, now about 1.5. So as you're again farther away, the pressure will be smaller, and also the impulse will be smaller. This is station number 8, which is at 90 degrees on the side, and clearly a tremendous reduction, because instead of 10 to the power of 9, now we're looking at 10 to the power of 8, okay? So a much lower pressure. At the same time, also in terms of the time axis, this is very small. You are looking at 0.2 milliseconds, but the pressure is coming a little bit later to this station, which is located at 90 degree on the side of the cylinder. Okay. So again, so this gave us confidence that our tool can analyze an underwater explosion subjected to a cylinder. But this cylinder has a unique property. And what our goal was at the end of the day was looking at reinforced concrete columns, and I'll explain why we're looking at that. So if you think about high-piled wharfs near our ports, they are usually very easily accessible. So if people want to do harm to this type of structures, it's actually very accessible. So we're tasked to generate pressure time histories for different configurations of reinforced concrete columns, circular columns, rectangular columns, and also at different standoff distances, also different explosive weights, also different depths of detonation. You may have a detonation near the air-water interface, or you may have a detonation at some distance within your water body, right? So the whole idea was to generate a matrix of pressure time history values for different combinations of the items I talked about. So for this particular case, what we did is we looked at one data set that's already peer-reviewed. Again, these researchers have done a test in a water tank, which is 10 meters in diameter and about 3 meters deep. They put a simple reinforced concrete column, filled the water tank with water, and detonated explosives. But these are very small explosives in the order of 1 kilogram. Okay, so we have this test data that's available for us. And also what they did is, because now they have a structure, they calculated what's called a reflection coefficient. Whenever you have a structure, the pressure actually will significantly increase compared to a case where you don't have a structure. It's counterintuitive, but what the structure does is, you will have a pressure coming, it will be reflected back, and then the shock event is also happening in time. So you will have more shocks summing together and hitting your structure again. So you have a lot of reflections coming here. And this is reported in the literature, so we have at least some guidance to check if our work is correct or not. Okay, this is one of our models, where as you can see, we have, it's very hard to see here, but we have a column. Can you guys see the boundary of the column here? It's a circular column here. And then we have an explosion at 50 centimeters from the face of that column. Okay. So as the explosion detonates, we're able to calculate our free field pressure. And then when the explosion hits the structure, we will measure what's called the reflected pressure. So our goal is to see what our simulation says about the reflected pressure divided by the free field pressure and compare it to the literature that's available in the Zhuang's test. So some of our comparisons are pretty good again. This is our result. Remember, at the free field, we can use empirical equations. This is the prediction from an empirical equation. Okay, so they're very close to each other. So relatively happy with our findings here. Now, when we put the structure, which is the column, again, 1 kilogram explosive at 50 centimeters, our method shows that the reflection coefficient, meaning again, reflected pressure divided by free field pressure, was about 2.1, whereas the Zhuang's experiment is saying 2.4. So our prediction was a little bit lower, but the challenge is, again, we did not do this test to say Zhuang is correct or not, right? So and we didn't do our own test also to see if we'll be getting 2.05. But again, very close without having our own experimental data to validate this work yet. Okay. So relatively close ratios between the two. Now, after that, again, we felt very comfortable. We can run simulations on steel plates or reinforced concrete columns. Here is one example for you that shows a good movie. On the left-hand side, what you see here is simply the density, so the red you see here is just water. Water has a density of 1 gram per centimeter cube. And then what you see here is air. And then maybe down here, I don't know if you can see, but there's an explosion starting here, right? Okay. On the right-hand side, it's just simply showing you the pressure generated at different points within the medium. Okay. For those of you who are interested to know more about the mathematics behind, there is a model called the 5-equation model: conservation of mass, conservation of momentum, conservation of energy, and then we have to come up with what are called equations of state. Different equations of state for the explosion, for the gas, because again, when the explosion happens, there will be a gas generated, right? So we need to have an equation of state. And also for the explosion itself, we have a famous equation of state. At least on the US side, we use JWL, Johns, Wilkins, I forgot the L, model. It's heavily, again, documented in literature. So then you may ask, okay, you have all these pressures generated, but what is the value of having those pressures? Well, at the end of the day, I have to be able to assess whether that pressure is causing damage on my structure or not, right? So once I have pressure, I have two options. I can take that pressure and take it to another program, which is heavily focused on structural response. And in this particular case, we explored a program called Abacus. So we took our pressure and put it in Abacus to see if this column, for example, is surviving that particular blast event. Okay. Now, this was not required by our sponsor, but we advise the students, so we do additional work to challenge our students. Okay. So in this particular case, you see a very simple reinforced concrete column. We try to model it as exactly as it's built. Well, you see the reinforcement, vertical reinforcement and stirrups. Okay. Now, our typical challenge in looking at structural response is understanding the behavior of concrete when it's subject to dynamic loads. How does it respond? This is the stress-strain diagram for concrete. So we do a little bit of study in our computer simulation to see how strong the concrete is, how it fractures for a given compressive load. That gives us the compressive strength of concrete. And once we determine that, we have the ability to relate it to other parameters that we need for our simulation. And then, of course, once we are comfortable with our material properties, we run our FE flow pressures at different times. So this is one example for you. Okay. And we have the ability to capture this pressure in time, in space, and transport it to the structural software. And this is, for example, it's a preliminary result. It's not necessarily correct, but it just shows you that you can apply the pressure and then now you see the column is bending, right? So there is a response generated by the pressure coming to your column. Okay. Our students are still refining their models. Another question that we typically get is, okay, you generate your pressure and take it to another platform to determine the damage, but can you do this in one platform? Can you generate your pressure and within the same platform, can you also predict the damage? And there are some softwares that will allow you to do that. One of the famous ones is called LS-DYNA. Now, the only challenge that we have with LS-DYNA is even if they are able to generate the pressures for you, you're relying on their capability to determine pressure. So you don't have a control whether that pressure is correct or not. We are not, again, trying to put a doubt on the particular software, but the ability to have your own software will allow you to predict pressure and validate whether the pressure is correct or not. Because if you make a mistake on the pressure, you'll be making a mistake on the response, right? So the previous approach will allow you to have more control on the quality of the response. Okay? But we are also conducting this, we call it coupled analysis, to see if the LS-DYNA approach is a better approach to do everything in one software. But if we say this is good, then we are running out of business, right? Because our program is FE flow. We have to look at the pressure also. So, but again, we're not gonna lie. I mean, we'll report our findings, but this is also your approach if you wanna do a study in a coupled manner. Okay, in conclusion, our objective for this particular project, what we were tasked to do was to expand an existing software at George Mason and build a capability to do underwater explosion. We actually just completed the project on the pressure side, but our students are still working on the structural response side as an additional project. This probably is my last slide. Blast and impact effects on structures. Studying it is still a vital topic. We need more engineers to look into these problems. Now, the good thing is I already have been working with, I clicked too fast. I have a strong collaboration with ITA. This is a test done here at ITA with Lieutenant Colonel Fausto, and now Anselmo is also doing, Major Anselmo is doing some tests. And this is a modeling that was done here at ITA with Major Anselmo. So we really have built a strong collaboration, and we hope to continue to collaborate with you guys. And I will always say thank you for my students, collaborators, colleagues, and project sponsors. Without their support, I mean, we can't do this technical work. And as part of, again, funding resource, I always put ITA because Fausto was at George Mason for 15 months. So that's an in-kind, support. So we appreciate that. Thank you very much. That's what I have for you. I know everybody is hungry for lunch. but I'll be happy to take a couple of questions. Please go ahead.
Hi, thank you for your presentation. Your last model you presented results based on incident pressure and reflected pressure. Considering the incident pressure is significantly greater than the reflected pressure, is there any significant difference in the results by taking into consideration the reflected pressure effect on the concrete columns?
Oh yes, actually it's the reverse. The reflected pressure is higher than the free field or incident pressure. On the order of at least 2 is what we have seen. So when you're doing, for example, equivalent simple degree of freedom models, you have to consider the reflected pressure.
So is there any point in analyzing the smaller pressure, since the greater one is already gonna give the result?
So maybe let me rephrase your question. Are you saying, is there any benefit to calculating the incident pressure?
Yes.
There is a benefit because that will give you at least the ground truth, right? For example, if I run my explosive simulation and I get a value that's when it was hitting the structure, if I get a value less than the incident pressure, then my analysis is wrong, right? So I think calculating the incident pressure is always good. At least it gives you the floor. And then you know that when you have a structure, your pressure will be higher.
Thank you.
Go ahead, sir.
Do you intend to extend the research to shade charts?
So, yes.
Detonation cord to blow off a shaft on a ship, or then they did research on torpedoes, how to buckle the hull of a ship with a torpedo, and I was wondering if you intended to extend that.
So our initial goal is really to, if we get funding, remember we are always dependent on funding.
NAVC.
NAVC. So if we get funding, we like to do our own small scale experiment, because we're relying on other people giving us the experiment. And some of the work is still there, but it's in a classified arena, right? So we have to navigate what's possible in terms of data, but we have the capability. I mean, we gave a temporary plan for our project sponsors where we can do a small scale tank type test, but we're really looking at more traditional explosives, not different, that would be for more a second continuation, right? But I agree with you that looking at different shape charges is important. Currently, we rely on the JWL model just to give us that expansion of pressure. But I agree with you, we should look into that too. And also, another thing based off of your question is, currently we are looking at just one explosion happening, right? You may have a series of explosions happening, so we haven't looked at that yet.
Morning.
Good morning.
I didn't see, there's a remarkable similarity of your 3 blue bullets in the only of your initial slides about how you treat this, predict or prevent, mitigate, etc. But I didn't see there one thing that is used with dams that predict when the hazard. If you could comment briefly on that, that would be a 4th bullet. But my main question is not, this is one, but the second and most important question is, we did a lot of finite element work, modeling structures, etc., thermal structures for satellites, I think, and also modeling asteroids, gravity fields of asteroids, etc. One very tricky question that's long, but I'll just let you comment on that. You didn't mention anything. You took 2 years to refine your finite element model. There are all sorts of tricks there. If you, the size of the mesh, the shape of the mesh or the elements, if you evaluate at center or extremes, etc., etc., etc. But it is especially true when you have a very fast phenomena. This is known in the aeronautical industry if shock wave equations in high pressure, precisely high pressures, 3,000 psi's, etc. So in aeronautical industry, people use evil rigs because the CFDs cannot represent, they are not represent the phenomena. Could you comment briefly on the fourth bullet?
Okay.
Prediction when dams will, this happened in Brazil twice, 2 dams. And they had the predictions algorithms. Second, the finite element tricks.
Okay.
Please.
Well, thank you for your questions. So for your first questions, in terms of predicting hazards, in the US, we have a software called Jesus. At least it tries to give you probability of, let's say, an earthquake occurring at a given zip code, or a probability of, let's say, a natural type event. Now, when it comes to terrorist acts, I don't think I have seen, I don't know if you can predict that. I mean, it could happen anytime. There is a center called the United States Bomb Data Center that actually will tell you how many explosions are occurring every day. And this could be like an explosion in a bank, in a restaurant. You can take a look at it and you'll be surprised. I mean, sometimes there is like 7 or 10 explosions in a day that they report. And sometimes you see no explosions, but there is a report. Every year they release out a report. There's a mechanism called tripwire where these things are reported. In 2022, to give you an example, there were about 15,000 explosive incidents in the United States. Now, when I say 15,000, doesn't mean all of them are leading to an explosion. But you can find some general information about explosions, but very hard to predict. For your second question, yes, finite element is a little bit challenging in terms of the amount of computational software that's needed. But there are so many, I think, developments in the area of refining. For example, the one model we picked, the 5-equation model, we have tested it significantly, and we picked it because it was giving us a better computational, it was requiring less computational resources compared to some of the advanced models like the 6-equation model, which may give you a very precise result, but you may be waiting an additional 2 months or 3 months to get the result. So I didn't bring all the mathematics here, but there's a series of papers we published in the top journals, like Journal of Computational Physics, that different mathematics involved here. So there's a trade-off between selecting your equations and having a quality result. And that's always a challenge, and I completely agree with you. But the good thing is all the simulations you see here, we didn't even use a high-performance computing. We used, of course, a very nice machine, but our students are using a simple workstation, which is a powerful workstation, but not high-performance computing. Thank you. All right, thank you very much.
Convidamos o tenente-coronel especialista em fotografia, Fausto Batista Mendonça, para realizar a entrega de uma homenagem e agradecimento ao professor doutor Girum Ugessa.